In this video, I'm going to talk about the query languages that are supported by the Myria Big Data Service. A major goal of Myria is to support multiple query languages within a single platform. We think this is good for users, as they can choose any language that's best suited for their problem, and it's good for research because it allows us to experiment with novel query languages while still supporting bread and butter query languages like SQL. What I've shown here is the Myria user interface, which can be accessed from a web browser. I've highlighted the Languages tab, which allows the user to select from among a set of supported query languages. Myria supports a variant of SQL, a query language called Datalog, and a new query language called Myriel that I will talk about shortly. On the right-hand side of the screen here are a set of example queries for each language. Okay? I'm going to click on this one that says Simple SQL Query, and then what we can see on the left-hand side of the pane is the sort of text that corresponds to sort of a basic SQL query where we're joining together two tables, a department table and an employees table, and we're trying to filter out and select the set of employees that make more than $6,000. Now, if you know SQL, this probably looks vaguely familiar, but there's a sort of couple of small interesting differences here. One thing that's interesting to note is that we support tables as variables, right? So you can do a select from where query and then assign that value to a variable and then use that variable as the input to another SQL statement, okay? So this is similar to how common table expressions work in sort of ordinary SQL, but we sort of like this sort of imperative style of programming a lot better. It's a lot less verbose and it allows you to sort of build up longer chains of programming logic without filling up your entire buffer. So we can go ahead and execute this query by hitting the execute button, and that will sort of bring up a result pane here on the right, and then this is a pretty small data set, so pretty quickly the query returns success. And one interesting property of Myria is that a single query can produce any number of data sets, right? For each one of these store statements, we'll produce one output, right? So in this case, I produced an output called SQL output, and if I click on the JSON button here corresponding to SQL output, I can see the result of my query. In this case, I had a really small data set and there were just 5 outputs. Somebody decided to put Magda in the accounting department, which is probably not the best allocation of our human resources here. All right, so if we're interested in gaining sort of a deeper understanding of our query, we can click the Parse button. And what this is going to do is show us the query plan that corresponds to this query. Okay, this is something that an ordinary user probably wouldn't do, but we're going to look at it here because it allows us to sort of dig in and get a deeper understanding of how the system works. Before you can understand this, I need to give you a little bit of background. So Myria is a parallel data processing system, right? So on the back end, we have a set of workers running across a set of machines. Each one of these workers has a slice of the data, right? So if there's n workers, each worker gets roughly 1 over n of the slice of the employees table and the departments table, etc., right? Okay. So the way to sort of read this a query plan is sort of from top down, right? So each one of these fragments more or less corresponds to a thread that runs on one of the workers, right? And so in each of these fragments, we're first going to do a scan. So this one's scanning the employee table, this one's scanning the department table. And then as you work your way down this query, what you see are these shuffle operations. And the shuffles correspond to moving data across the network, right? Ultimately, what we want to do is a join on these tables. We want to match up the employee's department ID with the department's department ID. But before we can do that join, we need to sort of hash the data such that employees with a certain department ID match up with departments with a certain department ID. And only once we've done that, can we actually apply the join. Okay. So that's sort of interesting. So what we can now do is look at a different query language. So I can look at the Datalog programming language here. And Datalog query language. And what I've done here is just simply translate the SQL query from the last screen to a query language called Datalog. And if you don't know Datalog, you can just sort of trust me here that this more or less expresses the same logic. We're sort of taking the employee table, we're joining it with the department table, and we're only interested in employees that make more than $6,000. And what's interesting here, if I parse this query, I get sort of more or less the same query graph here, the same query plan. There's maybe some syntactic differences here. But what's interesting is I can take a radically different query language, and they both sort of compile down to this same intermediate format. As I said, there's a third query language here, and this is sort of a query language of our own devising called Myria. One of the motivations here is that we work with a lot of users in the sciences, biology, oceanography, astronomy. These users come with a strong quantitative background, obviously, and they're familiar with sort of one or more sort of imperative programming languages, say R or MATLAB or Python, right? So they know how to program, and basic programming constructs are familiar to them, but SQL is kind of a foreign language, and Datalog is sort of way off their radar in terms of something they'd ever want to use, right? So we sort of came at this from the perspective of how would we design a query language that would be sort of more familiar and usable to this class of users, but we didn't want to throw out things like query optimization and indexes and all the good things that databases provide. So the result of that thought experiment is this language Myriel, and the best way to sort of introduce it is to look at one or more examples. And so what I've shown here is the same SQL query translated into Myriel. We're scanning departments, we're scanning employees, and then these two statements here where we express the sort of join and filter logic, right? So match up employees and departments and only give me employees where they earn more than $6,000. So if you're familiar with Python, this may sort of look vaguely familiar. These two statements, starting from line 4 going down to line 7, correspond to sort of something like list comprehensions in Python, right? And this was sort of intentional, right? We sort of envisioned programmers that were familiar with a Python-like language, and we thought maybe they would be well suited by this sort of syntax, right? Now, even though this language sort of looks vaguely like Python, it still parses down to something that is relational algebra. This sort of query plan representation is exactly what we saw in the case of SQL and exactly like we saw in Datalog, right? So you may be wondering what's sort of the value add here over a sort of standard programming language like Python. One clue here is if you look at how this query is written, right? So in line 4, I did the join between employees and departments, sort of match them up on department ID. And in line 7, I say, actually, I'm only interested in employees that make more than $6,000, right? So the filter step comes after the join step. But if you look at this query plan on the right-hand side, we can see that this selection where we toss out, we only keep employees that make more than $6,000, we do that step immediately, right? So we scan the employees, we read employees off disk, and then we immediately discard any employee making less than $6,000, right? So what's interesting here is that we were able to rearrange the order of these statements. In the program, the filter came second, but in the query plan that we actually execute, the filter comes first, right? This is something that databases have always done, but what's interesting here is that we can apply these sorts of optimizations in this sort of more imperative Python-like programming language. And this is something that a Python script can never do. Python will never take your statements and reorder them, but we can play these sorts of tricks because everything we do compiles down to relational algebra, and we know how to optimize relational algebra using sort of standard relational equivalences. One more feature of Myriel I want to touch on here is that it supports a form of iteration or recursion, right? So there's a lot of algorithms and programs where you need some form of iteration, basically a looping construct. Sort of one example here is a lot of graph algorithms like PageRank, where you assign each node a rank and then you sort of iteratively improve those ranks until you converge. Also, a lot of algorithms in machine learning are iterative, like k-means clustering, using gradient descent to compute logistic regression. Often you start with sort of an initial guess at a set of parameters and you iteratively improve that guess over a set of rounds, right? This is something that SQL is sort of not supported well, and even languages like Datalog have some iteration support, but only for limited classes of queries. So what I'm showing here on the left-hand side is how we've enhanced Myriel with this do-while construct. So anyone that's sort of taken an introductory programming class has probably seen something like this do-while loop, and everything inside the loop is sort of the standard Myriel language where we can express joins and group bys and standard relational operations. Okay, what this program does is an algorithm called sigma clipping. It's basically a form of outlier elimination. At each iteration, we remove points that are more than 2 standard deviations outside of the mean, and then we iteratively run that algorithm until it reaches a fixed point. That is, until it reaches a point where we don't produce any new bad points. Okay, so we think this sort of iteration construct sort of changes the game, and that it allows you to support a broader range of algorithms and programs and things like graph analysis, and machine learning. So to summarize, in this video I've given an overview of the query language support of the Myria Big Data Service. A couple of noteworthy things here. Myria is a multi-language system. We support multiple query languages that all compile down to a common relational algebra backend. And we're experimenting with a new query language called Myriel, which supports imperative programming and a do-while construct for imperative programs, which allows us to support a richer class of algorithms than databases have ever traditionally considered. Thank you for your time, and goodbye.